All right, so this actual topic is what we call applications of calculus to the physical world. So how we apply calculus. And really, I guess it's the initial reason why they thought of the idea of calculus, because they wanted to study the motion of planets, basically. So that's where it sort of evolved from. So again, let's talk a little bit more about this thing called displacement. We often use the pronumeral x in maths, because when we think about straight line motion, we tend to just imagine we're moving along the x-axis, just moving along a straight line like so. I think in physics they often use s for displacement. S because in physics they're silly. So all displacement is the distance from a point but with direction. And so the negative sign or the positive sign now means something different. All it is telling us which direction. So negative would be the left-hand side of the origin, positive would be the right-hand side of the origin. Velocity, strangely, we use v sometimes for velocity, but it is the rate of change. So the rate of change of displacement with respect to time, so it would be dx to t. Now, when we're talking about motion, another notation we sometimes use for the derivative is this dot notation. So one dot above the x means the derivative of x. That notation is only ever used in motion. So it's the rate of change of displacement with respect to time. So it's the speed, but with direction. So a negative velocity would mean I'm travelling in the negative direction. Positive velocity, I'm travelling in the positive direction. And then the third component, which is quite important, is acceleration. So different notation we could use. With A, obviously, for acceleration. But it is the change of velocity with respect to time. So it's the derivative of velocity. So it could be dv to t. But then that means it could be the second derivative of displacement. So you could write it as d2x to t2. Yeah. Then, using the dot notation, because it's the second derivative of displacement, you could have x with two dots. Or it's the first derivative of velocity, so you could have v with one dot on it. So there are all different ways you could have notation for acceleration. So the rate of change of velocity with respect to time. So displacement is distance with direction. Velocity, speed with direction. Acceleration, and this is the weird one, is acceleration with direction. We use the same word in both. So acceleration with direction. You may have heard this term of deceleration. There is no such thing as deceleration. Okay? It's often what people use when they say, hey, we're slowing down. But what deceleration is when you are accelerating in the opposite direction to which you are travelling. Okay? So if you imagine acceleration like a force, force equals mass times acceleration. Okay? So if you imagine acceleration as a force, and a positive acceleration, I'd be pushing someone in the positive direction. Negative acceleration, I'm pushing someone in the negative direction. So if I'm travelling in the positive direction, like I am at the moment, but someone pushes me in the negative direction, I'm going to slow down. But if they push me in the positive direction, I'm going to speed up. So when the sign is the same, I will speed up. When the signs are different, I will slow down. Some people mistakenly think, so negative acceleration is slowing down. No. Because if I'm travelling in the negative direction, so now I'm travelling in the negative direction, if I have a negative acceleration, someone's going to push me in the negative direction, I'm going to speed up. But if they push me in the positive direction, I will slow down. So slowing down, or this idea of deceleration, is when the sign of acceleration and velocity are different. One's positive, one's negative, and it doesn't matter which one is which. Okay, here's a neat little diagram I found in my first year of teaching, and I thought it was quite good, so I'm going to share it with you. Displacement, velocity, acceleration. To get to displacement or velocity, you differentiate. But if you want to go back the other way, if you want to go up, you integrate. Well, I thought it was good. Okay. Right, so here's our travel graph. Displacement versus time. Now, because it's a displacement, it's now possible to have negatives on my travel graph. Instantaneous velocity. What we talked about in the other one was average velocity. But average velocity is not that useful when you think about it. It was like that question where I said, what was its average velocity over the whole distance that it travelled? And it turned out to be naught, because we were back where we started from. How useful was that information? I mean, if you're driving in a car, and you're driving along and you started at home and you drive and you come back home and you say, oh, well, what was your average velocity while you were driving? Oh, naught. I mean, it is. Okay? But that's not real useful, especially if a policeman pulls you over and said you were speeding. Oh, no, my average velocity is naught. I'm fine. All right. So what we're more interested in is instantaneous velocity. And that's where the calculus comes in handy, because that's what I was saying about the slope of the tangent. If we find the slope at that particular point, then that will tell us the velocity at that instant. So that's what we call instantaneous velocity. Okay. Well, that's a displacement time graph. From there, we could draw a velocity time graph. Now, how would we do that? Well, I'd just translate key pieces of information. I know that at 1, I've got a stationary point on my graph. So therefore, on the velocity graph, that would become 0. Yeah. What other things do we know? The point of inflection. What would that become on the next graph? So, hang on, I think someone said it. What did you say? Yeah, it becomes a stationary point. Because remember, inflection point, the second derivative would be 0. So in other words, the derivative of velocity is 0, so it would be a stationary point. And then we can see things like it's increasing when it's going up, so I know the curve will be positive. Decrease when it's going down, so I know the curve will be negative. The other thing is the shape of the curve. What type of curve does this look like, this typical up and down with 2 stationary points? It's a cubic. You differentiate a cubic, you will get... So we're expecting to see a parabolic shape. And so there it is. That would be the velocity time graph. And again, we could find the instantaneous acceleration by drawing in a tangent and finding the slope of that tangent, because acceleration is the derivative. And of course, we could draw our acceleration graph, again, now looking at the velocity graph and saying, oh, well, that's a stationary point, so it will become an x-intercept. Hey, this is a parabola. What am I expecting to see down here in acceleration? What is it? Linear, yeah, a straight line. So acceleration would look something like that in this case. All right, so if I wanted to work out distance travelled, well, it's 7 metres because it's the total distance. I've gone up to 2, down to -2. It looks like I'm finishing at around about -1. So 7 metres in total, as opposed to my displacement. My displacement is -1, telling me, hey, I've finished 1 metre, but in the negative direction from where I started. The average speed, okay, so the average speed would be 7/4, because speed would be distance over time. Average velocity, displacement over time. Okay, so this time, instead of giving us a graph then, they've given us just the formula. But that's okay, we don't actually need the graphs anymore, because we can use the formula and what we know about calculus by finding stationary points. When is it concave up? We'll find when its second derivative is greater than 0, those sorts of things. So we can use what we learnt with curve sketching without actually drawing the curve. So here's our formula for displacement, t³ minus 21t squared. We want to find the acceleration, so a formula for acceleration. Well, all the question's really asking me is differentiate it twice. And there we go. So velocity, differentiate it once. Acceleration, there's my formula for acceleration for this particular particle. So all right, we want to know when the particle is stationary. This is why it's so cool that they call it stationary points, because it just ties in so nicely here. Because the particle is stationary when the velocity is equal to 0. Well, velocity is the first derivative, and stationary points occur when the first derivative is equal to 0. So it all ties in beautifully. So when is our velocity equal to 0? And by the way, don't leave out sentences like this. You're explaining what you're doing. And we're at the point now where if we're solving these problems, someone's going to come along. They don't want to see a whole page of numbers and that. They need to know what you're doing, what you're thinking. So particle is stationary when velocity is equal to 0. That's why I'm solving this equation. And I come up with two possibilities. So it was stationary initially, and then again after 14 seconds. Now, you might be thinking, if initially it's stationary, how on earth did it then move? Because here I am, I'm stationary. But that's all to do then with the acceleration. If you look at acceleration, when time equals 0, acceleration was negative 42. So which direction did I move initially? Where am I? Yeah, I've got to be negative. I'm stationary, and they're applying an acceleration in the negative direction, so I'm pushing them down. So initially, I'm moving off in the negative direction. And then after 14 seconds, I will stop. Now, after 14 seconds, if we look at acceleration, 6 14s minus 42, off the top of my head, I'm not sure what it is, but I do know it's a positive number. So I will stop, but now the acceleration is positive. Bang, I'll go back in the other way now. All right, once again, particle moving along our x-axis, starting at rest from t equals 0. But we're actually starting not at the origin, we're going to start at x equals 7. So its acceleration at time t is 2 plus 6t. We're going to find the position of the particle when t equals 3. So this time I've started with acceleration. I need to come up with a displacement formula. So we need to integrate. I've done it this time by finding a constant. So got to tie in the initial conditions. If you forget your constant in these problems, you're going to have a problem. Right? Because the constant is very important. So unless it works out to be 0, you're just going to get it wrong. We need something in here that links time and velocity. Starts from rest, time equals 0. So in this case, we would have got lucky. The constant did turn out to be 0. Okay. Integrate again. Now we're going to find another constant. Something that links displacement and time. Time equals 0. Displacement is 7. Sub that in. Our constant, in this case, is 7. There's our displacement formula. So now I can go and find when the t equals 3. T equals 3, sub it in. We're over at 43. So there we go. After 3 seconds, you could say I'm at x equals 43. I've written it as it's 43 units to the right of the origin. I mean, however you want to describe its position. Or, okay, dv to t, so I've written acceleration as dv to t. If I use the separation of variable ideas, then I could do it that way. So I split it up, so I have the t over on the same side as my t's, and my dv is all lonely by itself. On one end of the integral, I write the conditions I know, that when t equals 0, velocity was equal to 0. And on the top, this is the formula I'm trying to find, so t and v. And we just do it as a definite integral, and it ends up finding the constant for me straight away. In this case, well, it was 0, so it was a nice, easy substitution there. Then I could do the same thing. I could say velocity is dx to t. Again, I'll separate the variables. Now, this time, I don't actually have to go and find the final formula, because what I'm doing here is saying, hey, my initial conditions is that at time equals 0, x was equal to 7, displacement was 7. When time is 3, what is x? And so I can use that to work it out, because now, when I do my integration, on the left-hand side, I'll get x minus 7, and on the right-hand side, I get 3 squared plus 3 cubed, move the 7 over, and again, I get 43. So that is that idea of separation of variables, which can save a little bit of time in these sorts of questions. HSC question. Okay. Okay, 2001 HSC question. Particle moves in a straight line. Displacement in meters given by this. Ooh, very strange one. T is measured in seconds. What is the displacement when T is equal to 0? Okay, -1. That's a bit of a gift question there. Show that x equals 1 minus 4 on t plus 2. If you really want a gift question, now that's a gift question. Huh? In other words, break this fraction down. It's going to be 1 plus. All right. Oh, well, what do you know? 1 plus 4. Oh, well, that's the same as saying t plus 2 minus 4 on t plus 2. Oh, that works out. T minus 2 on t plus 2. What do you know? And hence find expressions for velocity and acceleration. So there's displacement, bit of differentiation, there's velocity, and there's acceleration. Is the particle ever at rest? So have a look at the velocity formula. Is the particle ever at rest? No. Okay. Because I've got a constant on the top of that fraction. That can never equal 0. So no, the poor little particle just keeps moving infinitely. Never stops. Poor thing. So give reasons for your answer. Well, that particular fraction can never equal 0, so it's never at rest. So what is the limiting velocity? The limiting velocity, remember we talked about that the other day? That's if time we could keep going to infinity, where would this end up? So I want the limit as t approaches infinity of velocity. So 4 on t plus 2 squared, that is 0. Or of course, I could just look at the graph. Velocity was 4 on t plus 2 squared. If I was to draw that graph, and I've just started the graph at t equals 0, but it would go down asymptotic to the, well, in this case, t-axis. So 0. All right, let's have a look at the next example. So 2002 paper, again, particle moving in a straight line. Time t seconds, its distance x meters from a fixed point. This time the function's far more interesting. Look at that. Sine 2t plus 3. The first question, I suppose it was just a clever way of sketching a trig graph question into the test, because now we have to sketch a graph of displacement versus time. So essentially we're just drawing a trig graph. So let's look for the key things we need. Amplitude will be 1. We've shifted the whole thing up 3. Period is pi. So I'll mark off my divisions every pi on 4. We've been told we have to go from 0 to 2 pi. So there we go. Now, because we've shifted up 3 and the amplitude's 1, so that's why on my vertical axis I've gone up to 4. But it also means that I won't be winding around the, well, in this case, t-axis. It'll be around the line y equals 3. So I'll just plot that in so I know where the what do they call it, axis. I guess that's what we call it, isn't it? Axis is. All right, sine curve. We'll start at, well, normally at the origin, but we've shifted it up 3. And then we go up, down, up, down, up, down, up, down. And there we go. There's our graph, sine 2t plus 3. Okay, using our graph, or otherwise, find the times when the particle is at rest and the position of the particle is at those times. And this is a case where or otherwise would probably be silly, because we can just read off the graph. We know it's going to be at rest at the stationary points, because that's when the first derivative, which is velocity, will equal 0. So when velocity equals 0, that means the derivative equals 0. In other words, the stationary points. So I can just read off. Well, pi on 4, and its displacement will be 4 meters, and then 3 pi on 4 will be 2 meters, 5 pi on 4 back to 4 meters again, and finally there, 7 pi on 4 at 2 meters. Certainly a lot quicker than solving the derivative equals 0. Describe the motion. I know you love these sorts of questions. Describe the motion completely. You know, you can sometimes see some lovely descriptions. Oh, it's a beautiful little graph. It's moving up and down in a lovely motion. How did I describe it? Oh, look at that word. Oscillates. Yeah. So the particle oscillates between x equals 2 and x equals 4, period of pi seconds. I think that's enough to describe what the motion's doing. Basically, it's just going backwards and forwards, backwards and forwards. The reality is, this is an example of what we call simple harmonic motion. But we don't know that yet, okay? But we will come to discover that later. So 3b